All right. So yeah, I'm going to be presenting on some recent work of mine about extreme particles for a interacting particle system called sticky Brownian motion. And this is all going to be joint work with Guillaume Barraquand. So our goal is we're going to study an interacting particle system where the particles evolve as independent Brownian motions where they're separated. And they stick together briefly when they're in the same position. And I'll say more about what that means in a bit. And we're going to prove that so think of this as a one-dimensional spatial system, and they're also evolving in time. So the rightmost particle will have fluctuations that follow a certain distribution called the Tracy-Widom GUE distribution. And this puts them in the realm of KPZ universality, where Carter-Parisi-Zhang universality class has certain predictions for sort of unusual fluctuations you see in certain systems. And that's the first thing I'm going to talk about is sort of what is the KPZ universality class. All right, so the outline of the talk, first we'll talk about what is the KPZ universality class. Then we'll define what I meant by this sticky interaction between particles. Then we'll present the result. We'll talk a little bit about why we care. And then if I have time, I'll say a bit about sort of what are the important inputs into the proof, sort of the important like starting points you need to actually get a proof. All right, so KPZ universality, Carter, Parisi, and Zhang are three physicists who sort of proposed some of the initial stuff in the 80s. So the KPZ universality class is a collection of probability models that have unusual fluctuation behavior. It includes models like fire spreading on a piece of paper or in a field, bacteria colonies growing in a petri dish, traffic in a one-lane road, random matrix models, the eigenvalues of random matrices in particular, interacting particle systems, directed polymers, and quite a few other models. And there's been recently a lot of interest in sort of the last few decades. So sort of the picture that maybe you should have in mind, this picture comes from an experiment where you have some liquid crystal where you have there's a region where it's unstable. It starts in an unstable state, and then if you heat it up, it'll jump to a stable state. And so they shine a laser at this central point, and it jumps to the stable state and releases some heat. And then you can think of it like it's burning. It's releasing heat and causing the stuff around it to jump to a stable state. And so these colors tell you how much time has elapsed. And so these sort of interfaces are the interface between the stable state and the unstable state after some amount of time has elapsed. And this is the type of one-dimensional interface that sort of grows randomly with time that we want to study. And so the way we'll talk about this is we'll say there's sort of a height function, which looks like your distance from the origin in the radial direction. And there's sort of a spatial direction x, which looks like if this were a circle and the angle were theta, x is like RD theta. It's sort of like travel a little bit around the outside of the circle. And there's also the variable time, which, this whole system is growing with time. And the typical system, the typical situation in KPZ universality, when you're looking at a boundary like this, is you expect the interface, this height function that depends on time and on spatial position x, to satisfy if we scale time like t and scale the position like t to the 2/3. At a particular point x, you expect that the boundary grows linearly outward with some deterministic rate a, and you should think of this as being like a law of large numbers. And we have sort of fluctuations in the height that are scaled t to the 1/3 and are distributed according to this Tracy-Widom GUE distribution, which I'll talk about a little more in a second. And you should think of this as being the equivalent of a central limit theorem, where, in a system where you have sort of everything's independent, you might expect that these are t to the 1/2 scale Gaussian fluctuations. But when you have sort of like the type of covariant structure you get in a one-dimensional growing interface with a few properties. You see t to the 1/3 scaled Tracy-Widom GUE distributed fluctuations. And to say what I mean by the with the Tracy-Widom GUE distribution, let's sort of give one example where it comes up, and a way to define it as well. So if you take an n by n matrix A with IID complex Gaussian entries, and we want to study the eigenvalues of these matrices, but we'd like it to be a one-dimensional problem, so we want the eigenvalues to be real. So we'll add the matrix to its conjugate transpose so we get something Hermitian. And then we have this ordered list of real eigenvalues. And if we take the size of the matrix, the side length, and we send it to infinity, then the largest eigenvalue will grow like, I'm going to multiply by root n so you can see the KPZ scalings. Root n times the largest eigenvalue will grow like something linear in n plus some n to the 1/3 scaled Tracy-Widom GUE fluctuations. And this is one way to define the Tracy-Widom GUE distribution. There's also some nice formulas, but I'm not going to dwell on that. Yeah, so this is when there's several conjectural things that models that sort of have this behavior should also have, but I'm just going to focus on this, and we're going to prove a limit theorem of this type. All right, so what is the system we're actually going to be working with? So sticky Brownian motion was introduced by Feller in the 50s. He was studying continuous Markov processes on the non-negative reals, which evolve like Brownian motions away from zero and have some boundary condition at zero. And what he ended up showing is that if you want it to be a continuous Markov process, the boundary condition has to be a mixture of three reasonably simple boundary conditions. So the three boundary conditions you're allowed to mix are killing, where when your Brownian motion hits zero, it's moved to a coffin state and you lose probability mass. You have reflecting, where when your Brownian motion hits zero, it bounces off immediately. And you have absorbing, where when your Brownian motion hits zero, it stays at zero forever after. And he introduced sticky Brownian motion as the unique boundary condition that interpolates between absorbing Brownian motion on one side and reflecting Brownian motion on the other. And there's actually a way to view sticky Brownian motion is sometimes called delayed reflection, because there is a way to view it as a time change of reflecting Brownian motion, where you basically, there's a way of slowing down time at the origin, so that I'm just going to say the local time becomes the actual Lebesgue measure time spent at the origin. There's a certain time change you can do where that happens, and that'll give you sticky Brownian motion from reflecting Brownian motion. But we're going to think about this a different way. So we're going to think about sticky Brownian motion with stickiness lambda as the weak solution to this stochastic differential equation. So there's going to be a unique weak solution to this equation. And what is this equation saying intuitively? It's saying that, well, first off, y lives on the non-negative reals. And so if y is not at zero, it just evolves like a Brownian motion. And if y is at zero, there's sort of no random piece, and instead we have a deterministic slope lambda if y is at zero. And I'm gonna abuse words and say y leaves zero at rate lambda to refer to this sort of slope lambda, despite the fact that it'll sort of leave and come back infinitely many times in small time intervals. So this isn't anything like an exponential rate, but I'll use the word rate and I'll put it in quotes. And so this is one way of sort of saying what the system is. Another way that is helpful for me in conceptualizing it is to say it's the limit of a certain discrete random walk that I'm going to call z epsilon of t. And what this random walk looks like is it's on the non-negative integers. If you're not at zero, it's just a simple random walk. If you're at zero, then at each discrete time step, you jump from 0 to 1 with probability epsilon times lambda, and you just stay at 0 otherwise. And so lambda is this stickiness parameter. And then what you do in the limit is you take the usual diffusive limit, where you scale t like epsilon to the -2 and space like epsilon, so that the simple random walk piece will converge to a Brownian motion. But notice that this epsilon, we're sort of tuning the behavior at 0 with the same epsilon we're using in our diffusive scaling. And this will give us, so that, and because of the scaling, instead of just getting a reflective interaction at 0, we'll get a sticky interaction at 0. And I like to think of it as the limit of this system. And if you want to see sort of heuristically why this slope lambda comes up in the stochastic differential equation from this discrete limit, you can just sort of think to yourself, it's law of large numbers in some time interval, in a unit length time interval. You have epsilon to the -2 chances to jump from 0 to 1, or from 0 to epsilon. So you jump epsilon distance, and you're going to take those chances epsilon times lambda proportion of the time. So if you multiply epsilon times lambda times the size of the jump times the number of opportunities, you get that intuitively you expect a slope of lambda when you're at 0. And sort of as a final warning in thinking about the system, I'll say that the set of times at which your system is at 0 is actually going to be positive measure with basically, if your system ever hits 0, the set of time it spends at 0 will be positive Lebesgue measure. And it'll be a nowhere dense set of times as well. So you could think of it as, obviously it's a random set, but you can think of it as being sort of the flavor of a fat Cantor set, or it's a positive measure nowhere dense set. And so maybe as a warning, this is a simulation that's based on this discrete approximation. And we're zoomed out pretty far, but and it looks like it spends a while at 0, but if we zoomed in, we just keep seeing smaller and smaller excursions. It doesn't actually spend any interval of time at 0. All right, so that's one particle that sticks to 0. Now, what we'd really like to do is to define an n particle system where the particles stick to each other. And to do this, let's talk, we're going to say that each particle, which I'll denote B superscript I of t, where I indexes the particles, will marginally evolve as a Brownian motion. So if we forget all the other particles, each particle just looks like a Brownian motion. And the sticky interaction means that if I take a pairwise difference between two particles, this will evolve as a Brownian motion sticky at 0, all with the same stickiness, lambda. And so if I wanted to sort of heuristically talk about what's going on, I could say that when I have two particles and they're in the same position, they want to separate with one of them going up and one of them going down at rate lambda, where by rate, I mean it in this sort of slope sense. And okay, that's what happens if two particles are stacked up. But because of this thing I talked about where you're going to have a positive Lebesgue measure of time, where like two particles are in the same place, you're actually going to see stacks of arbitrary numbers of particles in this system. And so you need to say what happens to uniquely characterize the law of the system. I need to tell you what happens when you have a stack of m particles, say like 5 particles all stacked on top of each other. At what rate does this split into smaller stacks? And these rates, theta k m minus k, are going to tell us, okay, I have m particles that are in the same position. What is the rate at which they split into k particles going up and m minus k particles going down? And so if you're told all of these rates, then that actually uniquely determines the law of the system. And this was developed, this sort of way of talking about n particle sticky Brownian motions was developed by Howitt and Warren in 2009. And they define everything in terms of martingale problems, which I will say a little bit about, but not sort of fully state because they get a little bit complicated. What I will say is that these rates, theta km minus k, you have a significant amount of choice. You have sort of infinitely many degrees of freedom in choosing them, but they do have to satisfy certain relations. And these relations basically come from the fact that you want your system to be consistent. And what that means is, I have a 5-particle system and it evolves according to these rules with these rates. And if I just forget 2 of the particles and pretend it's a 3-particle system instead, it should evolve according to the same law with the same rates. And this consistency condition gives you some relations on these thetas. And in particular, a nice way to package these relations is, sorry, does somebody have a question?
Excuse me, yeah, actually I do have a question.
Yeah, great.
So when the particles are not together, they are supposed to be independent, yes?
Yes. When any 2 particles that are not in the same position are evolving independently, and when they're in a stack, then they sort of evolve according to the same Brownian motion, but they have this sort of drift term extra drift term that causes them to separate at these rates.
Okay, so then here it's possible that indeed 3 particles stay together. When lambda equal to 0, it's kind of impossible. Yes, you 3, you hit.
Yeah. So because of this thing where the Lebesgue measure of the time that 2 particles spend together is going to be positive, you'll actually also see that in principle, the Lebesgue measure of the time that sort of n particles spend together can also be positive.
Oh, okay. Thank you.
Okay, thank you for that. Yeah, it's helpful to spell that out explicitly. Maybe I should do that. There's these relations these theta km minus k's have to satisfy. And a nice way to package these relations is we can take a random variable x, which is, forget that it says uniform 0, 1 for just a second, and pretend it's just x valued in the interval 0, 1. So x is any random variable taking values in the interval 0, 1. Then theta km minus k can be written as the stickiness parameter lambda times these expectations of x. And so, this for some x valued in the interval 0, 1, you'll get any possible thetas. So this sort of characterizes, you can characterize the different possible sticky Brownian motions by some measure x on the interval 0, 1. And so now we're going to make a very specific choice. We're going to choose that x is uniform. And we're going to make this choice so that we can get exact formulas for this system. That'll sort of be they'll sort of be the starting input for our asymptotics. And we're going to call these uniform sticky Brownian motions because these are uniform distributions, and it seemed like a good name. And how we came up with using these uniform sticky Brownian motions is that these are the limit of a certain model called the beta random walk at random environment, which I won't say much about, except that you can get similar exact formulas for that model. So that was why we chose this particular, that was why we made this choice. All right, and just to give a little more of a sense of, how you talk about these sort of like stacks of multiple particles. Well, first off, here's some pictures of 2 sticky particles, and 3 particles that all stick together. And now the way I've defined things, these particles are unordered. So, if they're stuck together, one of them can go up and the other can go down, or it can go sort of either way. But we can sort of rewrite the system as talking about the ordered particles, where sort of if you look at this picture, you see that sometimes the blue line, sometimes the blue particle is above the orange particle, and sometimes it's below it. But if we just say, okay, at every time slice, let's call these the y1, let's call green y1, orange y2, and blue y3 of t. If we make the x's sort of a new particle system that are just the y1s, but they're always ordered so they're decreasing. So now the top particle is always going to be x1 of t. The middle particle second largest particle is always going to be x2 of t. The third particle is always going to be x3 of t. And this is just sort of at each time step, we relabel the particles so they're ordered. Then it's sort of simpler to describe the evolution of this system. So when you're on the subspace where all the particles are equal, all the particles are stacked on top of each other, the way they'll evolve is they'll all evolve according to the same Brownian motion restricted to this subspace. So basically, there's some independent Brownian motion that drives all of them, and they all stick together. Plus, there's a drift term which pushes them out of this subspace, that pushes them apart, and it's going to look like 3 choose 1 times the theta 1, 2 times this vector, which is saying that the top particle has a drift upward and the bottom 2 particles have the same drift downward. So it's telling you that you split in a way where you have 3 particles coming in and 1 goes up and 2 goes down. And you have a similar term where 2 go up and 1 goes down. Hopefully it's sort of apparent how you would generalize this for a stack of n particles. You just have n choose k and theta k n minus k. Okay, so now let's talk about what we show. So the question we'll ask is, if I run lots of these sticky Brownian motions, what does the rightmost particle look like? How does it behave? And so here we've drawn sort of a picture of 50 IID Brownian motions and 50 uniform sticky Brownian motions. And we see that sort of they look quite different. Here it looks like you have 50 particles. On the right, it looks like you have, maybe 15 or 20. And what that's telling us is that they spend a significant amount of time stacked on top of each other. So we might expect to get different extreme values. We might expect that the outmost particle behaves differently in these two systems. And so first, the classical result for IID Brownian motions, which, this is a classical result, is that if you take n IID Brownian motions, and maybe the most classical thing to do would be to fix time and just let n go to infinity. But we're going to make a slightly weird choice where we're allowing time to increase, but n is increasing as some exponential of t. So if you look at the rightmost particle in this system, its position is going to look like some constant times t plus some logarithmic term plus some constant. This is all sort of deterministic piece, law of large numbers type thing. And it's going to have Gumbel distributed fluctuations that are constant order. And now the theorem we prove is that in our case, if we look at these uniform sticky Brownian motions, and you take the same limit where t is going to infinity, but the number of particles is growing exponentially in t, then you're going to get something that looks like a deterministic linear growth, which you think of as a law of large numbers. And then your fluctuations are going to be order t to the 1/3, and they're going to be Tracy-Widom GUE distributed. So remember that this is sort of one of the KPZ universality predictions, is that certain types of growth models should have this sort of behavior. And I'll say a little bit more about that in a second. And there's a technical restriction in this theorem that this slope has to be sufficiently big, or equivalently the alpha has to be sufficiently big that we have so that our slope is large. And this should be thought of as a restriction in the proof. We expect it to hold in general, but we can only prove it in this case. Are there any questions about what the theorem says, or anything?
Yes, as a sticky case, so that the constant C and the D obviously will depend on the lambda, yes?
Yeah. So the constants C and D, you can, we write down explicit constants, but I'm trying to sort of not draw attention to them. I'm trying to focus on the other things. Yeah, thank you.
I'm curious here, so the two results, the structure are kind of different. So when you send the lambda to 0, the C lambda, D lambda, that structure does not look like to converge to the IID case. So
Yeah. So
explain?
sorry, go.
Yeah, could you explain that?
Yeah. So there's a so there was actually sort of a follow-up paper that Guillaume wrote where he sort of does similar asymptotics as you're sending lambda to infinity as you increase t to try to understand. So you know, if you just commute the limits, if you just say, oh, first t goes to infinity, then lambda goes to infinity versus first lambda goes to infinity, then t goes to infinity, then it doesn't work. But he studied the case where you send t and lambda to infinity simultaneously.
Okay.
And he sort of found an interpolation between the Gumbel distribution and the GUE distribution.
Okay, great. Thank you.
Okay, thank you for the question. All right, so let's give one sort of other interpretation of this result. There's sort of another nice interpretation. And this comes from the fact that sticky Brownian motion can be viewed as a random walk in random environment. And what this means is that I'd like to sample sort of a random environment that tells me what my transition probabilities for an individual walker are, and then run n independent walks through this environment. And I claim that if I average over all possible environments and just look at the trajectories of the walks, what I get out is going to be the distribution of sticky Brownian motion. And in the discrete case, it's a little simpler to say what a random walk in random environment is because you just tell the probability of jumping up and down at each vertex. In the continuous case, you should think that the random environment is given by random transition probabilities. So, you know, if these were all just IID Brownian motions, then we would have some probability that at if you're at position X at time S, you transition to position Y at time T, and it'd just be a Gaussian. And in this case, we're going to say, okay, there's some coupled system of transition probabilities. So there's a transition probability for every S, T, X, and Y that'll tell me how a walker should evolve, sort of the probability that it goes from XS to YT. And now I'm going to sample all of these simultaneously, and that'll be my random environment. And this way of dealing with continuous random walks in random environment was sort of originally studied by Lejeune and Raymond in 2004. And other people have already shown that sticky Brownian motion satisfies it, so that you can use this description. So that was not one of our contributions. But if you use this interpretation, then our theorem can be stated as giving a large deviation principle for the quenched transition probabilities. So these are some random transition probabilities. And the claim is that for uniform sticky Brownian motions, if I look at the log of the transition probability from the probability that a particle starts at the point 0, 0, 0, so 0 space, 0 time, and that at time t it's above the line xt, then this should have this first term, which looks like a sort of a standard type of large deviation principle, where you have some something linear in t, and this thing is the max over theta of some function, and then you have t to the 1/3 scale Tracy-Widom corrections to it. And this is actually sort of the way that we formulate our results, is in terms of this random transition probability. And then proving the extremal value theory thing from this is actually is sort of quite simple, because they're sort of independent walks with this transition probability. So if you understand this transition probability well enough, you can say their behavior. And so, yeah, let me talk a little bit about sort of like what are the upshots of this. Why is this something we thought was interesting to study? So the first thing I'll talk about is the Brownian web, which is sort of another universal object with which several models converge to. And it's one way to see it is this the limit of a discrete system again. So you start with a sort of, think of the upward direction as time and the horizontal direction as space, and you're in the sort of the 2D integer lattice. And from each even integer, or for so I'm only going to sort of be interested in points that are 0 mod 2 if I sum their coordinates. The sum coordinates is 0 mod 2, just so parity works out. You can kind of ignore that. So from each of those points, I'm going to start a random walk where it's a simple symmetric random walk where the steps are up left or up right. And these walks are going to coalesce. So whenever two walks meet, they stay together forever after, and they just become a single random walk. And you can take a diffusive limit of this system to arrive at the Brownian web, which is sort of, which is intuitively, you would describe it as you take 1D Brownian motions starting from every point in space-time and they coalesce, but it's sort of not, it is not immediately obvious that this limit should exist, but you can take that limit. I refer to the discrete model because it's sort of easier to see that this is a real thing that exists. But you can take the limit and you arrive at something called the Brownian web. And so the connection between Brownian web and sticky Brownian motion is that a way of constructing the random environment for sticky Brownian motion is to look at a Brownian web and say, okay, my walks are just going to be paths through the Brownian web, except that at certain special points, so sort of loosely, if I look at this point, there's sort of a path coming in down here, and there's a path exiting, and then there's another path that starts over here. And if my walk had taken this step and that instead of this step, I would be on this path instead. I would have gone to the right instead of to the left, and I would have followed sort of another trajectory. And if I look at this branching point and I do sort of a diffusive scaling, then all three of these points are going to get sort of smushed together into one point in the continuous limit. And so it's going to look like I have a point where I have one path coming in and two paths exiting, and the path coming in exits to the left. But this path sort of also starts from the same point in the diffusive limit. And these are the sorts of special points I'm talking about. And essentially what you do is you do something where you allow at these special points your random walkers to, instead of jumping the direction the paths actually went, to make the sort of little jump over here and then follow the other path exiting that point. And so there's a way of putting a measure on sort of like on sort of how likely when a path hits one of these points, it's allowed to jump that way, to sort of exit from the other path than the one it started on. And this is a way of constructing the continuum random environment for sticky Brownian motions. So you just say sticky Brownian motions are sort of independent random walks through a Brownian web where they're allowed to go either direction at certain special branching points.
Mark,
and yeah.
I'm sorry, I have a question. This is Peter. Can you tell us about the initial conditions you're putting on your
Oh, yes. The initial conditions for us are that they all start from 0.
Okay.
So we're considering the special case where they all start from 0. And that corresponds to considering this transition probability from 0 to above the point xt.
Okay, I was puzzled with your picture of the web, because there it seemed I couldn't see how those started all in the same place.
Yeah. So the Brownian web, you start a Brownian motion from everywhere, but then if you want to run sticky Brownian motions through it, essentially, what you do is you can start Brownian motions from whatever points you want. You can start like 20 Brownian motions from 0. And they'll run through the web. And if you just ran them through the web, that would be deterministic. They'd all, or not deterministic, but they'd all evolve exactly the same way, right?
Given the environment.
Yeah. So once you fix the web and they all run through the same web, they're all just going to stick together forever. And so the extra thing you add is this thing where when you hit certain types of branching points, you're allowed to follow either the path you came in on or the other path that starts at that branching point. And there's some sort of coin you flip that allows you to switch.
Okay, thank you.
And those coins are independent, but the web is the same.
Yeah. Okay, thanks.
Great. Thank you for the question. So yes. So the reason, so one reason we're interested in this result is that the Brownian web is the scaling limit of several models we care about. Basically, if you take any random walk in random environment that has a non-trivial scaling limit, that has a non-trivial diffusive limit, it'll be one of the sticky Brownian motions for potentially different thetas than we talked about. And so they're all connected through the Brownian web. And also there's some other models for population genetics, like the voter model, that are where if you take a limit, you get something that looks like the Brownian web. And so our result connects the Brownian web to the KPZ universality class. And this confirms a prediction of Sun, Surtzer, and Swart in 2017. And you could use this sort of connection, if you were willing to, commute limits in a very non-rigorous way, you could use this connection to sort of predict that there might be connections just to other models converging to the Brownian web, to the KPZ universality class, and sort of like draw out some predictions from this that we could then try to prove. So that's one reason we care about this. Another sort of more direct reason, more sort of physical reason you might care about this is sticky Brownian motions have been used to model particle evolution in a colloid by Miranda Cerfon-Holmes. And if you're thinking to yourself, why would particles in a colloid evolve as sticky Brownian motions instead of just sort of independent Brownian motions? We can imagine, I'm going to talk about something that's not a colloid. I'm going to talk about pollen particles in water because Brownian motion. So if we have a bunch of pollen particles in water, and we're thinking the pollen particles are what we care to model the trajectories of, and the water particles are just the microscopic background that's sort of like the driving noise, too small to see. Then you could ask the question, what happens when two particles are very close together, two pollen particles? And one thing you could predict is that you get just independent pushes from the microscopic background. Just no matter how close the particles are together, the microscopic background is just pushing them in completely independent directions. And then these should indeed evolve like independent Brownian motions. Another thing that sort of seems plausible is that, at least in certain systems, when the pollen particles, the mesoscopic particles, are sort of touching each other or very, very close together, the pushes from the microscopic background might be correlated, might be sort of like the water in this region tends to go in one direction, or maybe in some other system, maybe water doesn't do this. And in that case, you would expect to see a sticky interaction for the particles if they get sort of like almost the same push when they're right next to each other. And a third thing that might happen, which is the thing that Miranda Cerfon-Holmes actually studies, is you could have a small scale interaction between I guess I called them pollen particles, so I'm stuck. But if they had some kind of like slight electrostatic attraction between them, or something. So when you don't have too many water molecules in between, they want to stick together for a little bit, then you expect them to evolve as sticky Brownian motions. And that's what Miranda Cerfon-Holmes was actually studying. And so there's sort of a natural question, which is, I give you an explicit physical system in the real world. Should we model the particles as evolving as IID Brownian motions or sticky Brownian motions? And our result suggests an experiment you could run to tell between these two cases, to tell which more accurately models the particles. And what you would do is you would take a tube that was very thin, so that the mesoscopic particles had to go one at a time, so they couldn't sit two next to each other, so that you get a one-dimensional system. You want to put in a whole bunch of particles at the left, and then you want to wait until the first particle exits the tube at the right, and time how long that takes, time that exit time, and then run the system a bunch of times so that you can get some estimate for the variance of the exit time. And the classical result and our result together say, okay, if the variance is constant order in time, then these are behaving like IID Brownian motions. And if the variance is order t to the 2/3 in time, these are behaving like sticky Brownian motions. So a fairly vague estimate of the variance will suffice. And I'm being a little bit loose here. Technically, we only proved this for uniform sticky Brownian motions. But sort of the KPZ universality conjecture sort of suggests that there should be a large family, at least, of sticky Brownian motions that have similar behavior. And so this t to the 2/3 variance might could be useful to tell between these two situations. And in fact, I believe Ivan has a grant to try to run an experiment like this, and we'll see how it goes. All right. So yeah, so let's talk a little bit about what goes into the proof. Before we do that, does anybody have any questions about anything happened before? All right, cool. So let's talk about a little bit what goes into the proof. So there's sort of 3 pieces of the proof. The first is coming up with a moment formula for the quantity we want to consider. And then there's sort of a special way of summing it, or you sum the moments to get the Laplace transform, but there's a very nice way of doing it so that you get a nice formula for the Laplace transform. And then you use the method of steep descent to take a limit of that formula to get your asymptotics. And so I'm going to focus on the moments because that's sort of the reason we chose this specific interaction between particles was so that we could get moment formulas. So remember that the quantity we want to look at is this quantity. And so this is the thing we would want to take moments of. And I'll just say that when you sort of shift in time, it doesn't change the distribution of this quantity. So if I went from minus t to 0, it wouldn't change the distribution of this quantity. And when you shift in space, it doesn't change the distribution either. So if I went from minus xt to the line 0 infinity, it would have the same distribution. And so those are the moments I'm actually going to consider, where now instead of having sort of just a single starting point and raising it to the power k, we're going to look at having k different starting points. And that shifting is just because when the starting points are different, this is actually like you can compute this quantity, but not the other one. But when they're the same, they're just the same quantity. And so the moment formula we prove is that if you take ordered particles, so x1 is greater than x2 is greater than is greater than xk, then this moment is given by a nested contour integral formula that looks like this. And this sort of nested contour integral formula comes a lot in KPZ universality. So I want to try to give, like, not the specifics of this case, but a little bit of intuition for how you come up with this type of formula. So yeah, I had these theta KLs. It tells you what happens when a bunch of particles are on top of each other. And we also know they evolve as Brownian motions when they're separated. And if you sort of FOIL out what this means to give you sort of a differential equation that these moment formulas should satisfy, the fact that they all evolve as Brownian motions when they're separate will tell you that when all the particles are separate, the moments should just evolve like the derivative should just be the Laplacian, sort of like usual Brownian motion stuff, usual generator for Brownian motion. And then the stickiness condition when you have 2 particles stacked on top of each other will end up telling you, giving you a boundary condition of this form. So if you have the I and the I plus 1 particle are in the same position, then some differential operator applied to this function should give you 0. And in principle, if you had like 5 particles, if you had 3 particles stacked on top of each other, there should be another boundary condition that has to be satisfied. There should be another condition that has to be satisfied. And when there's 4 particles stacked on top of each other, there should be another condition. And when there's 5, etc. But the special choice of thetas that we made allows us to makes this model beta-unsought solvable. And what that means is that basically the 2 particle boundary condition tells you that all the higher boundary conditions are also satisfied. So if you satisfy this 1 particle and this 2 particle, it tells you that all the higher particles boundary conditions are satisfied. So we just need to solve these 2. I'm actually being a little bit loose, and I'll give you a caveat at the end of this whole discussion. I'm describing what happens in the standard case. So the special choice of weights mean that we just need to solve these two boundary conditions instead of having a whole bunch more. And now how are we going to do that? Well, if we look at this blue term, this product is just the solution to this first equation with we impose no boundary conditions. We just want to solve this equation. So this gives us a solution to this equation for each W. And it's just the product of all the one-dimensional equations, or all the one-dimensional solutions. And so any linear combination of solutions like this, any integral over W's, is still going to be a solution to this equation. And then if we want to solve the two-particle boundary condition, a thing that you see happening a lot in KPZ universality is so we chose this to be sort of a contour integral formula where you have several different contours, and you have this red cross term. And the red cross term, it's not obvious in this case, but this residue on the bottom, when you have when B is I plus 1 and A is I, this residue on the bottom is what's stopping you from just deforming the I and the I plus 1 contours to be the same. So if you got rid of this residue, you could just deform them to be the same. And so we sort of set up this formula in exactly such a way that if you push this differential operator inside the integral and act on this blue thing, you get a term that exactly cancels this denominator. And so now if the xi and xi plus 1 are the same and you apply this boundary operator, you cancel this pole and you can push the I and I plus 1 contour together. And then you notice that in that case, this integral is the integrand is antisymmetric in Wi and Wi plus 1. And so the integral becomes 0. And this is, I'm not sure how understandable that discussion was, but this is the thing that happens a lot in KPZ models. Sort of beta ansatz is one of a few standard ways you can get integral formulas. So this is the thing you see a lot. The caveat in our case is that these continuous formulas is actually hard to show whether you have a unique solution or not, because this sort of weird type of boundary condition. And so we use the fact that this is a limit of a discrete model, and basically use the beta ansatz there and then push it through to this case. And just very briefly, what the proof looks like is we take these nested contour integral formulas for the moments. We deform all the contours so that they're all a single contour, and we pick up a bunch of residues doing that. We write the Laplace transform using a Taylor expansion, right, in terms of these moments, and we can simplify this right-hand side to see a Fredholm determinant, which is basically sum over k of k-fold integrals. So the kth term is a k-fold integral. And then you use the method of steep descent to analyze the asymptotics of these integrals to get a formula for the limiting object. And this is like a classic plan for how you would prove these sort of Tracy-Widom fluctuations. This is something that you see in a lot of exactly solvable models. And I'm going to say, sort of as a follow-up question, it would be interesting to understand whether this KPZ universality holds for all sticky Brownian motions, sort of all the parameters theta KL you could choose, and for all random walks in random environments. Really, we've shown sort of like, we've shown for uniform sticky Brownian motions it holds at these specific thetas, and we know that for the beta random walk in random environment it holds. It would be very interesting to see what other models it holds for. KPZ universality, you sort of expect it to hold for a wide class of these models. And there are some results of that flavor in other cases a little bit, but it would require significantly different techniques. And thank you. This is the paper that this talk is based on. And here are some of the references that would be sort of like very helpful in understanding sort of the setup of the sticky Brownian motions, or sort of like how you deform these nested contour integrals and sum them up. Thank you.
All right, cool. Thanks very much. So I'll do my claps, and everybody else can clap if they want. Are there any questions from anyone?
I had one when you were showing results about the extremal
Mhm.
behavior comparing